Hi everyone, welcome back to the channel. Today we are going to discuss about common source MOSFET amplifier. We have a N-channel enhancement MOSFET and we are going to talk about DC analysis to confirm operating region, and also we are going for the AC analysis to calculate the gain of the voltage. Let's get started. Here we are considering VDD equal to plus 15 volt and the resistor R1 as 200 kilo ohm and resistor R2 as 100 kilo ohm and the drain resistance RDS 2 kilo ohm and the source resistance RSS 1 kilo ohm, and the threshold voltage of N channel MOSFET will be 1.8 volt, and the transconductance of the MOSFET will be considered as 360 milliamps per voltage square, and we are considering all coupling capacitor as 10 microfarad. All right, let's break down the DC biasing analysis step by step, and let us assume our MOSFET operating in saturation region. To prove that, we need to confirm VGS, the gate to source voltage, should be greater than threshold voltage, and we need to confirm this drain to source voltage should be greater than VGS minus VTH. To begin our analysis, we will focus on DC behaviors of the amplifier. This means that we are looking at how the circuit operates with a constant or unchanging voltage and the current. This is a scenario we treat all the capacitor will be in the open condition, and effectively we are removing from the circuit. This leaves us with the simplified circuit that allows us to determine the quotient operating point of the MOSFET. First, we will simplify the circuit. For the DC analysis, the capacitor acts as a open circuit, and we will remove the input signal, and also for the load resistor and the bypass capacitors. This leaves us the final circuit will be like this. It's a common source amplifier, so that the VS is connected to the ground terminal. Here R1 and R2 provide a voltage divider network, and we need to find the gate voltage, and the gate voltage determined by the voltage divider formed by the R1 and R2. That means the voltage at this node, the VG is equal to VDD into R2 divided by R1 plus R2. If you plug the value, the VDD is equal to 15 volt into R2 is equal to 100 kilo ohm divided by 100 kilo ohm plus 200 kilo ohm. So which is equal to 15 divided by 3, and when we simplify this we will get 5 volt. So that our VG, the gate voltage VG will be the 5 volt. And we are assuming that this is the saturation region, so that the drain current in the saturation region, the drain current ID will be equal to Kp into 0.5 into VGS minus VTH whole square. And also we know that the source voltage Vs is equal to ID into Rs. Okay, the source resistance Rs, which is equal to the ID into 1 kilo ohm, and the gate to source voltage VGS is equal to Vg minus Vs, that is equal to 5 volt minus ID into 1 kilo ohm. And now we'll plug the value of VGS into the equation of ID. Then the drain current ID is equal to 360 milliamps divided by voltage square divided by 2 into 5 volt minus ID into 1 kilo ohm minus 1.8 volt, that is a threshold voltage, the whole square. And if you simplify this, we will get by applying the quadratic equation, we will get two values of the drain current, that is ID is equal to 336 milliamps and another value will be id is equal to 069 milliamps. And already we have discussed the value of vs is equal to id into rs. For example, if you consider this is the one value of id and this is another value of id. If you consider this value, which is 3.336 milliamps into 1 kilo ohm, we will get VSS as 3.336 volt. So the value of VGS is equal to VG minus VS. So we know that VG is equal to 5 volt minus 3.336 volt, and we will get the output as 1.664 volt. So if you want to prove the saturation region, the VGS should be greater than VTH. In our case, VTH will be 1.8 volt. So this condition will not satisfy. Let us consider another value of ID. That is equal to ID is equal to 3.069 milliamps. So that Vs will be equal to ID into Rs, which is equal to 3.069 volt. Our so that VGS equal to 5 minus 3.069 volt. When we simplify this, we will get 1.931 volt. So that our the VGS value is greater than VTH. So this condition will satisfy the saturation region. Now the condition number 1 got proved. Similarly, the value of VD is equal to VDD minus ID into RD, which is equal to 15 volt minus the ID 3.069 milliamps into 2 kilo ohm, which is equal to 15 minus 6.138 volt. When we simplify this, we will get 8.862 volt, and then we can call it as the VD. The drain voltage is equal to 8.862 volt, and similarly, the value of VDS is equal to VD minus VS, and we know that the value of VD is equal to 8.862 volt minus 069 volt, which is equal to 793 volt, and we need to confirm the second equation, or the VDS is greater than or equal to VGS minus VTH. We know that the value of VDS is equal to 5.793 volt is greater than or equal to 931 volt minus 1.8 volt. So which is equal to 131 volt. By considering this, the value of VDS will be the greater than VGS minus VTH. So we have satisfied the both condition, that is VGS should be greater than VTH, and the VDS should be greater than or equal to VGS minus VTH. Then we can conclude that this N-channel MOSFET operating in saturation region. Now we will go for the AC analysis to calculate the gain of the amplifier. For AC analysis, this capacitor C2 and C1 and the CS act as a short circuit, and we need to analyze the small signal module of n channel transistor. Now let us switch gear to the AC analysis. We'll use the small signal model for our MOSFET. So we need to visualize the AC equivalent circuit. Here the drain voltage VDD and VSS will be connected to the ground, that is AC ground, and the capacitors C1, C2 and C3 will be acting as a short circuit. We will use the transconductance model, which includes a voltage controlled current source, and here Vin is the input source voltage, and R in, we can call it as R3 as a source resistance. By considering this node, the R1 and R2 is connected in parallel because this VDD and VSS are connected to the ground, and the output side, the output side, anyway this capacitor will be short circuit, so that we can consider this as a short circuit, and this C2 will be in the short circuit mode. So the drain resistance RD and the load resistance RL is parallel to each other, and the final simplified model will be like this. The VGS is the voltage between gate and the source. The input side, we are applying VI as a source voltage through the C1 resistor, and the resistor R1 and R2 parallel to the ground, and the input impedance of the amplifier is approximately equal to ZI is equal to R1 parallel to the R2, which is equal to 200 kilo ohm parallel to 100 kilo ohm, which is equal to 200 kilo ohm into 100 kilo ohm divided by 200 kilo ohm plus 100 kilo ohm. So when we simplify this, we will get 66.67 kilo ohm. The input impedance of the circuit will be 66.67 kilo ohm. Similarly, in the output side, the drain is connected to the VDD through RD1. Output is connected to the capacitor C2. In the AC equivalent circuit, the drain resistance RD is parallel to the load resistance RL. So that the load resistance RL dash is equal to RD parallel to RL. That is equal to 2 kilo ohm parallel to 10 kilo ohm. Okay. Then 2 kilo ohm into 10 kilo ohm divided by 2 kilo ohm plus 10 kilo ohm. And when we simplify this, we will get 1.667 kilo ohm. So we need to calculate the transconductance GM of the n channel MOSFET at the TC operating point, so that the GM is equal to Kp into VGS minus VTH, that is equal to 360 milliamps per voltage square into 1.931 volt minus 1.8 volt. When we simplify this, we will get 47.16 milliamps per voltage. And let us calculate the voltage gain of the amplifier circuit. So that voltage gain of the amplifier circuit VA is equal to V out by V in, which is equal to VGS divided by V in into V out divided by VGS. Here the VGS divided by VI means V in is equal to ZI divided by ZI plus R in, and the output voltage Vout is equal to minus GM into VGS into RD parallel to R, because we are measuring the voltage between node D and the ground, and the current has to flow from node D to the ground, but in this case the ID will flow in the reverse direction, so that we have considered minus GM here, and the drain current ID is equal to GM into VGS. If we consider both, the voltage gain AV is equal to ZI divided by Rin plus ZI into minus GM into RD parallel to RL. So that is equal to minus GM into ZI into RD parallel to RL divided by Rin plus ZI. When we substitute the value, we will get the gain is approximately equal to minus 78.61. And there you have it. We have successfully analyzed our MOSFET amplifier and confirmed its saturation operation and calculated the voltage gain. Remember, the understanding both the DC bias and AC analysis is crucial for designing the and analyzing the amplifier circuits. Here gain is negative. It indicates an inverting amplifier 180-degree phase shift, and the source resistance Rin reduce the gain slightly compared to the ideal voltage source. The gain is determined by the transconductance GM and parallel combination of RD and RL, and the voltage divider effect at the input. Let us verify this in the simulation. By considering this circuit, we have VG, the voltage at this node will be 5 volt, and similarly the voltage between the gate and source will be 1.93 volt, and the gate to source voltage approximately equal to 5.79 volt, and the drain voltage VD will be 8.66 volt, and the source voltage Vs will be 3.07 volt. The drain current ID will be 3.07 milliamps. If you found this video helpful, please click on subscribe button and like the video and hit the notification bell for the more electronic tutorial. Please let me know if you have any question in the comment section below. Thank you for the watching.